it's here. Okay, so now I'm recording. All that stuff is due, and it's in the schedule in BB Learn, and also the due date is in the assignment name somewhere. If you need extra tutoring resources, there's only one person left. Who am I looking for? Tyler Shepard, yay. I don't know where Jacob is. Okay. The Student Success Center, you can find them through the NAU website. They have tutors available. If they don't, tell them to just contact me. I'll find somebody good. IEEE, generally there's people in there who know what they're doing and they'll help you out. And I will help you out during office hours. I'm much calmer this semester because I'm not overloaded, I can think. It's good. Yes, last class we learned how to solve differential equations using finger paints. I have my stylus now. Hopefully it'll look a little bit better. Does anybody in here remember recess? Oh no.
Oh yeah, I watched that when I was super little.
Okay, this was a show that was on when my kids were young. I loved it because it was like what life was like when I was a kid. Amazingly accurate. It was one of my son's favorite cartoons. These are for those of you who don't know, these are the kindergarten kids who have self-organized into their own little terrifying village. You don't want to go there. They're scary. Let's finish up second order circuits. We're getting there. So this is one of my key slides. And generally, I'm gonna have this listed out, the procedure. But first thing you want to do is figure out if it's series or parallel. And then you can calculate alpha using the component values. You calculate omega naught. You determine the type of damping. Is it critically damped, over damped, or under damped? And once you do that, you can figure out the form of the response. This will be the answer. If you're looking for IL, it'll look like that. If you're looking for VR, it will look like, it'll still have the same form. If you're over damped, you need to calculate S1 and S2, and there's the equation. S1 is associated with the plus sign. You'll get the wrong answer if you don't do it that way. I just learned to accept that. If you are under damped, you will also need to calculate omega D. Okay, so then we move on from there. You're gonna have to figure out, to get A1 and A2 in those equations, you're gonna have to figure out the initial conditions. The V or I of 0 plus, and the rate of change of V or I at t equals 0 plus. That'll involve a little bit of circuit analysis, but you know everything else. If once you know those, you know everything else in the equations except for A1 and A2. You have a system of 2 equations and 2 unknowns. The equations are different for overdamped, critically damped, and underdamped. That's the only part of this slide I ever use. Okay, then we move on. In order to get these numbers over here, the V or I of 0 plus, and the rate of change of V or I at 0 plus, you're gonna have to do a little bit of circuit analysis. And it starts with this, the most basic equations in the world. I equals C dV dt, V equals LdI dt, and V equals IR. We can find the rate of change of voltage across the capacitor by just solving for that and plugging in T equals 0 plus. Same thing, we can find the rate of change of current of an inductor pretty quickly. And for an resistor, this is just the derivative of Ohm's law Ohm's law. If Ohm's law is true, the derivative is true. Things that will help you, you can get these 0 plus values, or some of them, by realizing a capacitor cannot change its voltage instantaneously. So if I draw that 0 minus circuit, I can find, I know VC of 0 plus. And I also from the 0 minus circuit, I can get IL of 0 plus. These down here, they don't have any relationship. The current through a capacitor can change instantaneously. The voltage across an inductor can change instantaneously. And since resistors don't store any energy at all, they can change like all the time. Okay, now this is bugging me. I don't know how bad of faces I'm making. Okay, so that is it. And the circuit analysis part. We know the initial conditions. This is what we want. If we're solving for VC, we need this. If we're solving for IL, we need this one. Series circuits always share the same current. This is the part that's tough for people. They share the same current. I know I've done this a lot of times, but I'm going to do it again. If they have the same current, the rate of change of their currents has to be the same too. So generally when I'm starting out here, I know VC of 0 plus and I know IL of 0 plus. I get those from the 0 minus circuit. I know one current, I know them all. Yay. That is a wonderful thing. Now, since I know all the currents, I know the current through the resistor also. It's got to be flowing in the same direction. That's why the positive sign of that resistor is going down, because current's flowing into that node. I can calculate, I can just use Ohm's law here and calculate VR equals IL, because it's the same, times R. Once I get the voltage across the resistor, I'm going to use KVL, which is going to tell me, going around this loop, the way the pluses and minuses are going, VR plus VL plus VC equals 0. I know VR and I know VC, I can find VL. And then I can plug that into this equation. I can plug IC into that equation. Now, if it's a parallel circuit, they're a little bit different. Parallel, we know they share the same voltages. We still know VC and we still know IL from the 0 minus circuit. Since I know VC and it's in parallel, I know VL, I know VR. And again, I'm going to jump to the resistor because Ohm's law gives me this little bit of information that makes everything else possible. Ohm's law is going to tell me that we know IR equals VR over R. So we can get IR. Then we can use KCL, Kirchhoff's current law, otherwise known as Gazzenta's equals Gazzata's. What goes into the node equals what goes out of it. All three currents are going out of the node, so the sum of those three currents as they're drawn is going to equal 0. I know two of them at this point. I know IR and I know IL. I can solve this for IC. That's the key to getting these derivatives here and then plugging them back into those equations. Okay, so we're going to do about 3 example problems today. That's enough. don't complain. And that's the plan. These are going to be circuits where we're not given the initial condition on the voltage. So we have to go back to that 0 minus circuit and figure out what they are. And when I write an exam, and I've done this a lot of times in here, this is the part where students have the most trouble, is finding those initial conditions. So this is a good good place to pay attention because we're going through the whole problem. The whole problem's too long for one exam. So I break it up into parts. Okay, so here's our general procedure as we've kind of figured it out. We've been doing it like this, but this is my consistent way of always doing it. My first question, is the RLC in series or parallel at t equals 0 plus? So I have to look at the circuit and determine that. Once I figure out if it's series or parallel, I calculate alpha and omega naught, and I compare the two of them to figure out what type of damping I have. Once I know the type of damping, I can calculate S1 and S2 and omega D as needed. If it's over damped, I need S1 and S2. If it's under damped, I need omega D, and that's on that first one of the key slides. And there's formulas for them. They're on slide 11. Let's just jump back and look at it. See, if it's over damped, there's S1 and S2. If it's under damped, there's omega D. So I just calculate the ones I need, and if it's critically damped, I can just skip that step. Then we write down the form of the solution, and the form of the solution again comes from this key slide. It's right here. If I'm looking for IL of t, I say IL of t equals form. If I'm looking for VC of t, I say VC of t equals that form. So once I know the type of damping, I can figure out which of these three forms of the solution that I have. Next step is the part everybody has trouble with, so it always ends up on the exam. Use circuit analysis to solve for what we need here, I of 0 plus, or the rate of change of I, the voltage, or the rate of change of voltage. And we'll go through a lot of 3 examples of that today. That's a lot. Okay, you know the type of damping, and since you know the type of damping, you can look at this and say, I'm going to write down these equations. If it's over damped, I write down this pair, critically damped, the pair in the middle, and under damped, I write down that pair. I've already gone through the step of figuring out what the voltage, initial voltage is, and the initial rate of change of voltage, so I can plug those in. I've already calculated S1 and S2 and alpha and omega D, so I can plug those in. And then I have 2 equations and 2 unknowns, A1 and A2. I do a little bit of algebra and I'm done. Write down your equations and then solve them. Once you get to this point, you go back to the form of the solution from 4 and fill in the known quantities, A1, A2, S1, S2, omega D, whatever's in there, alpha, whatever's in there, and you are done. Don't forget to put units at the end. It matters. It could be amps, it could be milliamps. It makes a big difference, and it could be volts, and I do take points off for that. I grade my exams myself because it's the only way I have to keep in touch with what you guys are actually learning, especially now that I can't see your faces. We'll get back to that soon enough. Yeah, I just didn't want to slog over to Frankie in the snow. It's still, there's parts of campus that are still pretty icy and everything, so we'll start class next week. Okay, so this is a finding initial conditions problem. I think I want to do this in bamboo paper because I actually wrote this up. The only thing here for this circuit that looks kind of strange you haven't seen before, this current source says it's 4 U of t amps. And remember, U of t is that unit step function. So we graph it like this. It goes from 0 to 4 amps at time t equals 0. So at 0 minus, it's going to be 0. And at 0 plus, it's going to be 4 amps. And we want to find all this stuff for the circuit. So let's switch to bamboo paper. And touch it a couple of times and it'll open up. Ah, there it goes. You have to move you guys for a minute. Everybody lean up for a minute. Okay. And then lean back down. I want you about right there. Okay. So the first thing we have to do when we're solving for initial conditions, we've got to draw the t equals 0 minus circuit. To solve for VC of 0 minus, which equals VC of 0 plus, IL of 0 minus equals IL of 0 plus. That's what we're looking for in this circuit. So that U of T source is 0 amps, which is like deactivated. When you deactivate a current source, you get an open circuit. So I'm just going to leave it open. And it's been sitting here a long time. So I'm going to put in the DC model for both the capacitor and the inductor. So the capacitor was over here. I'm going to just leave it like this. It has a voltage across it. It's open circuited, but there's a voltage there. That 30 ohm resistor is still in the circuit. And the inductor is now shorted out, but it has a current going through it. Okay, so I want to solve for VC and IL and then use them later. The capacitor is open, so no current can flow this way. All the current has to go through the 30 ohm. And it goes through the 30 ohm. It's also got to go through the inductor. So IL is pretty easy. This is about how easy most of these are. Of 0 minus equals 5 amps. Okay. If we want to find the voltage across the capacitor, I'm going to put currents flowing into the resistor. So I'm going to put a plus here and a minus there. I can find the voltage across the resistor using Ohm's law. It's in series with IL, so it'll be the same thing as that. Times R, 5 times 30 gives me 150 volts. Now, I'm looking at this. The combination of the inductor and the resistor are in parallel with VC, so the sum of those two voltages has to equal VC. Some of you see that. If you can't jump to that conclusion, you could always write KVL around this loop, and you get VC minus VR, and we'll put the inductor in here, minus VL equals 0. VL 0 because it's a short, so VC just equals VR. VC of 0 minus equals VC of 0 plus equals 150 volts. So these are the two things we really wanted to, no, please, thank you. No, wait. I'm not frozen. That's at least that's at least a good part. These are the two things we wanted to get out of this part of the analysis. We got the 0 plus and the 0 minus. Now we're going to draw the 0 plus circuit and plug these values in. So you can go back to the slide and look at it, but at t equals 0 plus, the big change is that source that was 4 U of t now becomes a 4 amp source because it is switched on. Yeah, I've had a change in the circuit. So I'm going to draw the inductor back in. I know the current in the inductor is 5 amps. That can't change. My resistor was up here, R. And my capacitor has some value, and it has a voltage of 150 volts across it. And that 5 amp source was DC, so it's still in the circuit. Okay. What we want to get from this, and what the slide asks you for, is all the voltages and currents in this circuit. So what I need is I need IL. That just equals IL of 0 minus. And that we've already solved for, 5 amps. I'm going to need IC. This is what you're asked for. I'm going to need IR. I'm going to need VL. I'm going to need VC. We know VC because it doesn't change. This is going to be 150 volts. And we want to find VR. When I look at this circuit, R, L, and C are in series in the 0 plus circuit. So this would be a series RLC. Now, what can we find? How do we get there? Diddy-dum. Okay, I'm going to put my plus sign on my resistor. That's semi-arbitrary. At this node right here, I'm going to write a KCL equation. We'll call this 1. The reason why this is easy for me is because I've been doing this for years. So KCL at 1, current would be flowing that way in the resistor. Currents going in are 4 and IR. And the current flowing out is 5. So IR must be 1 amp. I'm going to write that down on my little list so I know what I've solved for. Okay. If I know, oh, somebody's chatting. I'm actually doing this. Yeah, okay. All right. We've got IR. We can find VR just using Ohm's law. So VR equals IR times R. And what was R? 30 ohms. We've got 1 times 30. This gives me 30 volts. I don't have a passive sign convention violation, so I don't have to make that negative. So VR 30. No. Okay, good. It's 30 volts. Thought I locked up again. Okay, IC. I like KCL. We're going to do KCL at 2. We know IR. We've solved for it. It's right there. It's going out. The current through the capacitor will be going this way. Passive sign convention goes into the positive. So going into the node, I have 5. And going out of the node, I have IR, which is 1, plus IC. So we can get IC. IC is 4. Okay. All we have left to find is VL. I can, what I'm gonna change colors. Oh, my color wheel is behind you guys. Everybody lean to the left. Red. Lean back, everybody lean back to the right. Okay, so I'm gonna do KCL around this loop right here, this inner loop, because I already know 2 out of the 3 voltages. Be careful with the signs. Current goes into the positive terminal. I'm gonna start here and go clockwise. So VL is my unknown. This is KVL around that loop. Whatchamacallit, VL. And it's positive because I'm going from minus to plus as I'm going clockwise. R is also going from minus to plus, so it's positive. VR, we know what VR is, so let's put that in, 30. Minus VC, because it's going in the other direction, and VC is 150. It's the signs that kill you guys on this. And I get minus 120, I move it over to the other side, I get VL equals 120 volts. One of the labs, it's part of lab 2, has this problem in there that has a sign. I'll talk about it later. We'll talk about it when we get there. So we got VL 120 volts. Okay, I've got everything I need to proceed. I've got all of these, and I have them written down on a piece of paper. Did I get that wrong? I have a sign error?
I have a question.
Yes, thank you.
Shouldn't it, do you have IC going down across the capacitor? If you have 5 amps going into node 2, and then you have
5 amps going.
Yeah, going into node 2,
Right.
and then you have IC going down, shouldn't it equal IC equals 5 plus 1?
5. Okay, so they're both going out. The current through the resistors, I've drawn it, is going out of node 2, and the current through the capacitors, I've drawn it, is going out of node 2. So that I think that is correct. It's 5 equals 1 plus IC.
Oh, okay, so 1 amp is going to the left?
Yes.
Okay, all right.
Yep. According to this, I have a sign error. What did I do wrong? I defined IR in the other direction, so that's not really a sign error. Oh, I just changed my definition of polarity for the resistor. Not really going to affect the answer. What I would do is, if you came up with this list on your exam, and I had -30 and -1 on IR, I'd check your polarity up here. And if your polarity was different from mine, it's still right. And my old solution has a different polarity from my current one. So we're just going to run with this. So it's still not wrong. So we've got these values. I'm going to change this on here just to remind myself. I changed the polarity. Now we want to find the rate of change of all this stuff at t equals 0 plus. We want to find the derivative of all that. Okay, let's move on. What I want to find here is let me just do this with prime so this doesn't take forever. I want to find IR prime at 0 plus. I want to find IC prime at 0 plus. And I want to find IL prime at 0 plus. I also want to find VR prime at 0 plus, IVC prime at 0 plus, and VL, the other one, at 0 plus. Now there's a couple of equations. Remember I equals C dV dt. So we know okay, thank you. VC prime of 0 plus, dV dt equals I of 0 plus divided by C. Now we've already solved for I of 0 plus, and we wrote it down neatly, thank goodness. It was 4 amps. So this is just 4 divided by the capacitance value, whatever the heck it was, 4 over C, but it comes out to be 108. And this will have units because it's the rate of change of voltage will be volts per second. So we use that little formula, we got one of them really quick. 108 volts per second. The other formula that I can use fairly easily, V equals L di dt. So I can get I prime of L at 0 plus just equals the voltage across the inductor at 0 plus divided by its inductance. We were good and we saw for the voltage at 0 plus. So this is 120 over whatever L was, and I didn't write that value down. But the prime comes, and then the answer comes out to be VIL of 0 plus is whatchamacallit. Where is it on here? IL prime. It's 120. Oh, it's 3 henries. So it's minus 40. Wait, why was it minus? No, it's positive. I'm right. It's 40. It's a rate of change of current, so it's going to have units of amps per second. Okay. The derivative circuit, I've got 2 DC sources in there. Those DC current sources are not changing. If I draw the derivative of the circuit, if you guys just be, I have an inductor. It's got a current rate of change of 40 amps per second. I'm going to continue my swap on this, on my resistor, my sign swap. The solution has a sign in the different direction. And I have, what do I know? I've got 40 amps per second going through there. I know the voltage across the capacitor is changing by 108 volts per second. Okay. It's a series circuit. Everything has the same current. Everything has the same rate of change of current. So if I follow this current line through the loop, it's going into this node of the resistor. It's still 40 amps per second. So yeah, I know all of these. It's a series circuit. I can plug these in. Series, currents are the same. The rate of change, the derivatives of the current are the same. Okay, since we have IR prime, since Ohm's law is true, the derivative of Ohm's law is true. VR prime will equal IR prime times R. We've got IR prime as 40. Our resistor is still 30, so this becomes 1200. It's a rate of change of voltage, so it's volts per second. Okay. Only thing left to find is this little puppy right here. And I'm going to use KVL. If KVL is true, the derivative of KVL is true. So the rate of change, we know this one is 1200. Going around the loop in this direction, I have VL prime. Still going uphill, plus 1200, which is VR prime, minus 108, which is VC prime, all that has to equal 0. We get VL prime equals negative, no, it's not negative because it is, I defined it in the other direction. It is positive 1092 volts per second. If you do it this way and you do it methodically and you have to do it like this in one of the lab sections, what you're going to get is if I wanted to solve for IR, I've got IR and I've got IR prime. It's written down. I could put those down. I could find their A1 and A2. Same form of the solution, whether I'm looking for IR, VR, VC, VL, whatever. The thing that's going to change is the A1s and A2s. Did we take it that far? So we found the initial conditions. That is one step. If we wanted to complete solving this problem, we still have to find alpha and omega naught, which we haven't done yet. We need to determine the type of damping. We'd find the form of the solution. We'd find S1, S2, and omega D is needed. Look at those equations, find A1 and A2, plug in the values, and we'd be done. That's one problem. Look at the chat. Why? Oh, Gerardo. In my solution, it is negative because I defined the, whatchamacallit, let me see if I got it right. You're right, Gerardo. It's like that. Let me put it here. VL negative. You can see what I did.
Jordan Ramirez wants to know if these type of RLC circuits can be done using superposition or source transformations.
Yeah, you could, but yeah, you can use anything that you've learned in 188, but it's not going to help you. In this case, for this particular circuit, it's not going to help you much. Because you could have put it in the frequency domain. Oh, I see what you're saying. Like using phasers. They're DC sources, so phasers don't work. They're switching circuits, so phasers don't work real well. We're going to have a discussion about this in the next class. Because we're going to talk about different methods of circuit analysis that you've used. You could try to apply those, but it's not going to work really well with this circuit, just because it's a switching circuit. And I'll talk about why later on. When we get to frequency response, we're going to go back to something that looks a lot more like phasers, like you did with AC analysis in 188, except it's not going to be at a single frequency. It's going to be across a range of frequencies. And then all those rules from 188 apply. I can see the chat lighten up. It must be freezing. Why would I go to Texas Roadhouse? Oh, yeah, I can tell. I don't know if they're open in particular. They have been open in the COVID restrictions because one of my students works there. I've never been there.
In this redrawing of the circuit,
Yes.
is it kind of just like a rule of thumb that when you're doing the rate of change or the derivatives of the components in the circuit, you can ignore the sources that were there before, or were you just doing KVL?
Okay, no, this is why I'm doing it. That's a good point. So I have this this is at 0+. I have the 4 amp is in there because it's already switched on. I have the please don't, okay. I have the 5 amp in there because it's been switched on. But the rate, these are DC sources at this point. The rate of change of this DC source is 0. That's why I took it out. The
'Cause
rate
it's
of change,
constant,
yeah, it's a
staying.
constant. So that's why I annihilated them.
Okay, thank you.
That's literally the derivative of the circuit. Sometimes I just make this stuff up. Or I haven't seen people do it like that before, but it is correct. Okay, so let's go back to the slides. We've done this one, we've done this one, we have done that, we've talked about this one. Finding the solution from here is going back to this general procedure. Okay. What was my next thing? My next thing was to, yes, yeah, remember the key slides. We've talked about these today already. Okay, so here is another one. We're gonna go through the whole solution for this one. It's a little bit simpler. The first thing I have to do is sort out what this means on the current source. This is U of minus T, which looks like this. I think this one showed up in an exam at one point. I haven't put that on for a while. It's 4 volts before T equals 0. This is time. This is the voltage axis. 4 volts, and it's 0 volts after T equals 0. So in the 0 plus circuit, it shows up. In the 0 minus circuit, it doesn't show up. What do we want to solve for? What the heck did I'm not going to do all that, Dr. Brower. I want to find, it's way more. What, are you serious? I'm going to solve this for VC of T. Let's keep this a little bit simpler. So we're going to solve this for VC of T. Okay, so first thing I want to do is find the initial condition. We're going to actually go through and let's do it. Do you want to do it in order according to my procedure or not? I don't know. It'll work for you. Okay, so I've got the circuit at T equals 0 minus.
Wait, so Professor, we are doing it according to your general procedure?
I have no idea at this point. I'm doing the initial conditions first. You want to do it?
Okay.
Do you want to do it according to my general procedure? I can change that pretty quickly.
I don't know. I just like being a creature of habit, and whatever habit I get into, whatever's the best way, that's just what I'll do.
Let's do it that way. This is the way I normally solve them anyways. Okay, so we'll skip the whole Dr. Brower thing. What we're going to do is we're for the 0 plus circuit. This is a parallel circuit. When I take that, well, they're parallel either way. So it's a parallel circuit. That's my first question. This is the way I like solving them. So it's parallel. We want to calculate alpha and omega naught. Omega naught is always 1 over the square root of LC. And alpha, we're on slide 17. Let's go back here. Alpha for a parallel circuit is 1 over 2 RC. So alpha is 1 over 2 RC. We plug in the values that were given, and alpha comes up to be 1. And omega naught comes up to be 5.1 radians per second. We just ignore the fact the units are different. Alpha is less than omega naught, so this is underdamped. I think this is about step 2. Okay, it's underdamped. We can go back to this slide, and alpha is less than omega naught. Yes, that's underdamped. And we get the form of the solution right there. And it is right there. So the form of the solution for VC of T, I think that was probably number 4 by this point, but anyways, VC of T is A1, which one comes first? Cosine omega dt plus A2 sine omega dt, all times e to the minus alpha t. We've got, and that has units of volts. We know alpha. The only thing we need that we don't have is we don't need S1 and S2. It's not in this equation. So let's solve for omega d. And I forget which order they come in. Did I put it on here? Yes, I did. Omega d, we could go back. You can actually go back to this and say omega d equals, that's the formula. And you can bring these formula sheets in on the exam. Just shrink them down and get them on your note sheet. Omega d is omega naught squared minus alpha squared. So we plug in the numbers we've already calculated for omega d and alpha, and this comes out to be 5 units or radians per second. Okay, so we got that far. Now we have to figure out what A1 and A2 are. I know in that equation what I'm going to need from the circuit analysis is I'm going to need, oh, thank goodness. My pen, every time my pen skips, I think my computer's frozen. I'm going to need VC of 0 plus, and I'm going to need dVC dt at t equals 0 plus, which equals IC of 0 plus over C. So really what I need to know is the voltage and current across the capacitor to solve this. I don't have to do all of them. So I'm going to go to the circuit and I'm going to draw it. At 0 plus, the current source is out. And because it's a 0 amp source at that point in time. I've got, wait, we have to figure out, before we can just stop, we've got to draw the t equals 0 minus circuit first. There's information we're going to get off of there.
Going back for just a quick second.
Sure.
Okay, thanks.
To get VC of 0 plus, I need VC of 0 minus is my issue. So I'm going to have to go to that 0 minus circuit. And at 0 minus, it's been sitting there for a long time. The current source is on because it was 4U of minus T. The resistor's 2 ohms. The capacitor has been sitting there for a long time. It's an open circuit. VC of 0 plus. And the inductor is a short, but it has a current going through it. So, got it. Okay. 4 amps comes out of here. It has a, it can't go through the capacitor. It has a choice of going through the resistor or going through a short. Which way is it going to go?
I have a
With the
quick
short.
question.
Sure.
For this example, wasn't the 4 also a step?
Yeah, it was, it would look like this for you of the minus T. So 4U of minus T is going to be 4 before T equals 0, and it's going to be 0 afterwards.
Okay, thank you.
Yeah, and right now we're looking at 0 minus. So you could do the current divide equation here, but intuitively when I see this, if I'm an electron and I have a choice of going through a resistor and a short circuit, I'm always going to go through the short. And if you do the calculations, it'll turn up like this too. The current through that resistor will be 0 because it's in parallel with a short. So IL of 0 minus equals IL of 0 plus equals 4 amps. Now, since none of the current's going through the resistor, there's 0 volts across the resistor. That's just from Ohm's law. These 3 devices, the capacitor, the inductor, and the resistor, are all in series, in parallel, so they share the same voltage. So 0 volts across the resistor means I have 0 volts across the capacitor. Okay, we've already found one thing that we needed for our A1 and A2 equations, and that's the big goose egg. Now, the other thing we have to get off of the 0 plus circuit, and that's the rate of change. So I'm going to draw the T equals 0 plus circuit. Now this 4U of T minus T source is at 0. A 0 amp source is like an open circuit. I have the resistor in here. It's 2 ohms. My capacitor is capacitating. That was the name of a band when I was in college. It was a bunch of electrical engineers at Auburn had a band when I was in the colleges called Mr. Resistor and the Incapacitators. Okay, you guys don't care.
I thought that was pretty punny.
Everywhere I went until I was like graduated college, I was a band person. I would get people together and make music for me. IL is 4 amps. It cannot change. And VC cannot change, so this is still 0 volts. So what we're shooting for here, let's look at the end goal here so we don't do too much work. We're looking for dVC dt at T equals 0 plus, and we know that is IC of 0 plus over C. So all I need to do is find its current. Okay. Well, I know how to get there. I've done this before. What we have here is we've got 3 devices in parallel. They share the same voltage. So the voltage across the resistor is 0 volts. If the voltage across the resistor is 0 volts, Ohm's law tells us the current must be 0. And then I can jump to KCL and say IC plus 0, they're all going out, plus 4 equals 0. So the current through the capacitor must be negative 4 amps. I can plug that into this equation. I get negative 4 over whatever the heck C was. What the heck was C? It was 1/4 of a farad. So this is negative 16. So these are the 2 things that I needed to know for my A1 and A2 equation. I didn't solve for everything this time. I didn't do it methodically. I just looked for what I needed. Okay, we got that far. We're going to figure out what the A1 and A2 equations are. Okay, so I'm going to go back and make sure. Yes, it's underdamped. Okay.
Is that negative 16 in volts per second?
Yes, it is. Thank you.
Or, yeah, okay.
Yes, because I do take points off for that. If it's a question on the test, if it's something specific I ask you for, I want units with it. If you're just doing the calculations, you can leave the units off. But yeah, and I don't ding you too. I try not to ding you too much. Okay, so it's underdamped. I've got this set of equations right here. V of 0 plus, if I was solving for I, it would be I of 0 plus. V of 0 plus is A1. Oops, what did I just do? VC of 0 plus is going to give me A1. And we already know what that one is. It is 0. Yay. And that would have units of volts if I get too particular. And the other equation is the rate of change of V, it's minus alpha plus omega D, minus alpha A1 plus omega D A2, before I forget it, equals VC prime of 0 plus. And we've got a number for VC prime. It was minus 16 volts per second. So this equals minus 16. We've got a number for alpha and omega D, I hope. Yes, we do. Alpha is somewhere. Alpha was 1. I plug that in. A1 is 0. Omega D is 5.1. And A2 is unknown. And that equals minus 16. So we can solve for A2. And A2, is that right? Oh. Or did I do that wrong? I think my solution's wrong. I'm arguing with myself here. It's alpha A1, omega D A2. Yeah, I'm wrong. Okay, so I have my calculator. There's a little slight error in the solution. What I'm going to get here for A2 is basically negative 16 over 5.1. Negative 16 divided by 5.1 gives me negative 3.14. It didn't look right. 4. And it's going to have units of, oh great, what the heck are the units?
Would
This,
it be volts per second for this one, since it's
yeah. Okay, I'm gonna think through this. This is volts per second, but omega D, it has units of, yeah, you're on the right track, Lauren, but it's okay. This has units of radians per second. Now radians are dimensionless, so I have to multiply it by the units of A2 times 1 over seconds has to equal volts per second. So A2 is actually in volts.
Okay, I see.
Okay. You know, and that is the same mistake I made the first time I was teaching this class. I know I did that like for an entire semester. The first time I taught it, I had a group of students that I had taught in 110 and 188 all in there. So they were kind of patient with me. So we've got A1 and A2. The next thing is we're going to go back and revisit the form of the solution. VC of t is A1, and I remember it this time, cosine comes first, omega dt plus A2. We may not even get to the third problem. Sine omega dt. This is the most time I've ever spent on this. E to the minus alpha t. A1 is 0, this term goes away. A2 is minus 3.14. Sine omega d was 5.1. T is my variable. E to the minus alpha. What the heck was alpha? 1 t. And this has units of volts. Good. We're done. It took me, because I had to throw all the words in too, it took me a better part of 20 minutes to solve that problem. That's too long of a problem to put on an exam, so I break it up into pieces. But make sure you know those steps and you know how to do it. There's 2 of these problems on the homework assignment. Keep that in mind. There are two at the front end are not quite as long, but there's 2 problems kind of like this on the homework. If you need any help, I'll be in my office. That's where I live. Let's see, where were we at? We were somewhere down here. We actually solved this. Let's go ahead and skip this one. It's in the slide solutions. It's just more of the same. Doing one of these well, I found, is much more effective than trying to race through all of these in the slides. Now for an overdamped system, I don't even want to talk about that. Oh, I think we're done. Overdamped. Yeah, overdamped. It's like they're approaching an exponential. Overdamp gives you the best stability, but it's going to take a while to get to the final value. Critically damped, it will settle the fastest. And underdamped have these sinusoids in here. Oh, I know I know why we're spending last 10 minutes of class. I had this planned. Underdamped, if it's getting more towards, this is getting more towards critically damped. The ringing, the variation, the sinusoids are starting to get damped out by this exponential function. There's a special case of underdamped systems where alpha equals 0. And when alpha equals 0, there's no damping and you get a sinusoid out of there. This is called an oscillator. It's a way of making a sine wave generator. And the way you get alpha equal to 0 is you take all the resistance out of the circuit. In theory, you can do this. So you just put an inductor and a capacitor in parallel, and you're going to get an oscillator. As long as you can keep all the resistance to 0. The wires have resistance though. So you need something to amplify this to keep it going. But in theory, this makes a beautiful oscillator. Which brings us to the next thing, which was, this is qualitatively what's going on. And I don't think you get enough of this. You need a lot of it when you're engineering in the real world. You don't get so much of it when you're in college. So let's look at this. This is if you really want to understand this stuff, YouTube has a whole bunch of. We'll just share the screen and shut up. Okay. And turn my volume up. Can you hear it?
Yep.
Okay. An inductor is a device. This is an oscillator. A capacitor is a device containing terminal plates. If we connect an inductor and a capacitor, oh, it's even closed captioned. The current and we call the frequency. Like one of my favorite extra credit questions. This frequency is determined by the value of the inductor's inductance and by the value of the capacitance. It's 1 over root LC. It's always 1 over root LC. Sorry. If the wires in this circuit hypothetically had no resistance, then these oscillations. On the other hand, suppose that our circuit consists of a capacitor. Once the capacitor discharges, the voltage across the resistance. This is what you did in lab today. In the circuit with the resistance.
Someone in the chat just asked if a perfect oscillator, you know, is possible to be made, or is it just like theoretical?
No, we built oscillators at Motorola. The trick is, let me stop this for a minute. The trick to making an oscillator is you have this resonant circuit, and the resonant circuit is going to amplify. It's got a little bit of resistance in it, but it's going to amplify everything at that frequency really well and attenuate at other frequencies. We'll look at some curves for this later on. So you put feedback in there, and feedback is a way of reinforcing the signal. So you put positive feedback in there, so you have some kind of amplifier with this oscillator circuit. And when it gets a little bit of signal at the frequency you want, you amplify that, and you feed the amplified signal back to the input. So you can keep on getting a larger and larger signal at the input, and eventually, like the voltage sources and things like that, will limit how far it will go. Oscillator design's kind of a black art. We'll talk about it a good bit when we get to frequency response. But for right now, the kind of the heart of that is keeping the keeping the signal strong through this LC network that has very little resistance, and then using an active device like an op amp to amplify that and feed the output of the amplifier back into the input of the LC. So it keeps getting a bigger and bigger input until finally it breaks into oscillation. The most common way to build a good oscillator is to try to build an amplifier. And if you want to build an amplifier, you try to build an oscillator, but that's a whole nother thing. Sorry. There's lots of videos like this on YouTube. I'm sure you guys can look at these yourself. Let's see if there's any more questions. Anything good? Okay, so for a tactile switch circuit instead of a throw, right? We could put an AC source instead of a switch. We could put a square wave generator instead of a switch. Generally, when we're actually building circuits, we don't want people to have to throw switches all the time. We want them to happen automatically, so we use transistor switches and we control the gates on those, and we'll get to all that. All right, we don't need to have a monkey pressing the switch all the time. I'll be the same before and right after. Yeah, once the switch is pressed down, the conditions, the current through the inductor would be the same right at that instance, and the voltage across the capacitor would be the same, but you could get large voltage spikes across the inductor, and you could get large current spikes through the capacitor. So this video going to be extra credit. Well, yeah, no, okay, so the reason why I did this is one of my favorite extra credit questions on the next exam. It involves oscillators. It's actually fairly simple, but never mind. Yes, the feedback recharges the capacitor, and it just puts a bigger signal. The feedback puts a bigger signal back onto there. So it's like that AC source in this video is coming from the amplified output of the LC circuit. So as you start out at level 1 and on the AC voltage, and you put that into an amplifier, it makes the AC magnitude bigger, and you put that back into the AC source. So this AC source is getting bigger, so that's going into the LC circuit, and it resonates and filters out the other frequencies, and it's getting a little bit bigger on the input, so that input goes into the amplifier, and then the output gets even bigger. And then that gets fed back into the AC source. There's a limit based upon what your voltage power supply is. Yes. Oscillators are sort of black magic, but they do work. And we'll talk about what causes them as we move along. Okay, it's time to go. The only person I have absent is Jacob, and I talked to him before class, so I know where he is. So I believe everybody's here. We'll get into next class. We're going to start Laplace transforms, and we're going to start looking at some of these circuits and how they behave as you change the frequency. So it's kind of like AC analysis from whatchamacallit 188, only done with multiple frequencies. Good stuff. Okay, I will see you guys on Monday. Hopefully in Frankie. There shouldn't be any snow. Okay. All right, we'll see ya. Stop share. Stop recording. I want to stop it.